In this video, we are going to look at the class example of differential rate laws, and it is on page 4 of your homework packet. All right, so I look at this equation, 2a plus b forms c plus d. I have a box of information, even though it's not boxed in. And let's see, let's try to determine the rate order of each thing. Now, it looks like I wrote an answer here, rate equals k a b, which means it must be first order in a, first order in b. How did I know it was first order in a? Well, if b was held constant in 1 and 2, 0.25 to 0.75, that's not doubling, that's tripling. Okay, so I should probably change that right there. And I could just say times 3. Okay, if this triples. And what's happening here, 4.3 times 10 to the negative fourth, 1.3 times 10 to the negative third, that looks like a tripling too. So if one triples and the other triples, that is first order. If this goes up by a factor of 3, this goes up by a factor of 3 to the first power, which would be tripling, then that's what happens. So it looks like experiment 1 to do. If A triples, should say triple there, as a reaction triples and B is held constant, then it will be first order in A. So we know that's a tripling instead of a doubling. I don't think I'm gonna write out that big word. I'll just put a 3 times right there. And I think the key I provide, I did make that correction. Okay, next thing is we got to figure out, how do we know what B is? I don't see any place here where A is constant. So what am I going to do? Well, I look between 2 and 3, and I see as A doubles, okay, if B was held constant, I'd expect this to double. But this goes up by a factor of 4. So I'm thinking, hey, if this is going up by a factor of 4 here, and A is causing it to double, then B, which is being doubled, must also be causing it to double. So essentially, this is going up for a factor of 4 because A causes it to double, and then B causes it to double, which causes combined factor of 4 effect. So in other words, A doubles as the reaction rate quadruples and B doubles. So both changes in A and B have a doubling effect in the reaction, which adds up to that quadrupling effect. So because doubling one doubles the other, the first order, we're going to say this is first order in B. It's having that doubling effect when it's doubled. Okay, so now we can say rate equals Ka times B. Write the rate law, we've done that, calculate the value of the rate constant. And I think I chose number 3 to do this. So I'm going to take these numbers, solve for K, plugging in these values, and this is what I get. And you can just kind of grind through the math to do that. And I put in units with doing that. Ultimately, a lot of times these questions are asked for units. It's molarity -1, minutes -1, which if the overall order is second order, 2 first orders add up to a second order overall. This is the typical form you'd see this in. Okay, let's see. The next reaction asks for something which might be a little bit confusing to figure out. Determine the initial rate of change of A in the experiment. All right, so I'm going to determine the initial rate of A. So this is really just asking us to look at the ratios here. What happens as A disappears, B disappears at half the rate, because twice as much A disappears. For every 1 part of B that disappears, 2 parts of A disappear. Or for every 2 parts of A that disappears, 1 part of C forms or 1 part of D forms. So based on not the rate law, but on the equation that we have here, the stoichiometry in the equation. So determine the initial rate of change of A in the experiment. We're talking about in the experiment 3 is the rate of formation is 5.3 times 10 to the negative third. So what's going to happen is A is going to be what? It's going to be double that, except it's going to be negative because it's going to be decreasing, or just instead of a negative sign, indicate that it's going to be decreasing. So I kind of showed this mathematically. Change in A over time is the same as -2, change 2C over time. So I have to double it because there's twice as much as A. and that negative just saying it says decreasing. You know, looking at how the question was worded, determine the initial rate of change. Yeah, you want to somehow either with a sign or state it that it's decreasing, but it's going to be twice as fast. You get rid of A twice as fast as you form C. So that is what I'm doing. I'm just looking at those ratios. And in D, we're asked to solve for a question mark. Well, we know this, we don't know this, we know this, we know K. So we know everything. We just have to plug things in and solve for a concentration. And hopefully your concentration will end up with a unit of molarity. That is what you'd expect. So plug in, solve that data. And then the last question asks, identify which reaction mechanism represented below is consistent with the rate law developed in part 1. Justify your choice right there. And what I'm looking at is, I'm going to try to see which one matches up. My rate law was A to the first, B to the first. Well, I look at the slow step though. Then I can say, oh, that matches up pretty good, but it's the fast step. I got to look at the slow step. Now, can I even substitute when there's a C? This would be confusing. I'm not quite sure where I can go with this. Let's look at this one. The slow step is here. I have A, I have M, but I can substitute B for M. So I said I got first order in B, first order in A. That looks good. Let's look at this one, M plus A. We do got a substitution for equilibrium. However, this would give me A and a B and another A that I have here. So this would actually fit better if it was a second order in A and first order in B. So I'm going to go with choice B. Now, the first thing I can say is once I choose this is these equations should add up to equal the overall equation. Usually it does. I cross out the intermediates here, intermediate here and here. I end up with 2A plus B forms C plus D, which matches my equation originally, like at the very top of the page. Okay, so that overall equation should match up to that. And then what should happen is the rate law of the rate determining step should match up to my rate law right here of rate equals KA times B. So here's how I answered that. The rate law of the rate determining step in 2 matches the overall rate law with the equilibrium substitution for n. In other words, rate Km times A becomes rate K prime, and it would be what I substituted the B in for the M, so it becomes B times A. So that would be the correct answer for this one right here. And again, I'm not too worried about the prime thing right there. All right, that is another example of in-the-box thinking with differential, the differential rate law in solving those problems.